Did you know that trees contain the same kind of compound as gasoline? It's true! When wood is heated to about 150 degrees Celsius, its cells start to break down and release volatile gases. You know these gases as smoke, but they're actually full of hydrocarbons, the same kind of molecule that you find in other fuels like octane and methane. When they're heated up enough, hydrocarbons ignite easily and burn really well, so if that smoking wood gets even hotter, those gases react quickly with the oxygen in the air and combust to form flames. That, friends, is Chemistry of Fire 101, and it's responsible for more than 100,000 uncontrolled chemical reactions, more commonly known as wildfires, in the US that together consume up to 3 million hectares of forest and brush every year. That's an area about the size of Maryland, burning annually. However, that's not entirely a bad thing. Fire serves a lot of important ecological purposes, and many ecosystems have adapted to make the most of it. The problem is that it's fire's job to destroy things, and when that encroaches on human territory, which is pretty much everywhere, we have a problem. Wildfires really are an amazing force of nature. They can leap across highways, create their own wind, and in certain conditions, move at speeds exceeding 30 kilometers per hour. Yeah, that's probably faster than you can run. And scientists are beginning to find changes in how and where wildfires are occurring. Truth be told, they're getting bigger and fast. It makes sense when you think about it, but every fire requires three things: heat, oxygen, and fuel. Foresters know this as the fire triangle, and wildfires will always spread in the direction that has the most abundant of these three elements. Likewise, the only way to put a fire out is to eliminate, or at least significantly limit, one of these things. The source of heat that starts a fire can be either natural or not, like lightning, a match, or an ember from a campfire. But which fuel actually ignites from this heat depends on a number of factors, including its moisture content, how much of it there is, even how it happens to be spread out over the environment. Light fuels, like grasses, leaves, and needles, tend to dry out and burn quickly. Heavy fuels, like the branches and trunks of trees, will take longer to warm and ignite. Either way, it's really the quantity of fuel that determines whether a fire can spread. And how about oxygen, the third point on the triangle? Well, air is made up of about 21% oxygen, and most fires require only at least 16% oxygen to get started and keep going. Put together, these three elements combine to form one of nature's most powerful, important, and transformative forces. Because even though we typically think of fire in terms of what it destroys, many ecosystems depend on it for renewal and maintenance. On grasslands, fires promote the growth of herbs and grasses and prevent trees and non-native plants from crowding them out. And fire has been such a constant part of forest ecosystems that a bunch of species have actually adapted to take full advantage of it. There's the jack pine, for instance. Its cones open when exposed to the intense heat from a fire, dropping its seeds into the ash-enriched soil. Every single living jack pine can die in the fire, but this adaptation makes sure that new ones will grow in their place. Forest fires also tend to stimulate the flowering and fruiting of many plants. And that's because wood ash is one of the best fertilizers around. It contains just about all of the nutrients that soils supply for plant growth, including calcium, potassium, and magnesium. And ash also acts as a liming agent because of the carbonates that remain after the wood burns. This raises the pH to help neutralize acidic soils. Fires also remove much, if not all, of the canopy, the uppermost layer of the forest. With that overhead cover gone, sunlight and rainfall can make their way to the forest floor. A nice open canopy can encourage other grasses and wildflowers to take hold while reducing the competition for water and nutrients in the soil. So I mean, what's not to love about fire? Oh yeah, the destruction. We like to call them natural disasters, but wildfires are almost always the result of human behavior. According to the US National Park Service, nearly 90% of all wildland fires in the US are caused by people, whether by illegal or unattended campfires, discarded cigarettes, or arson. Even sparks from power equipment and fallen power lines have been known to cause forest fires. But the remaining 10% of fires are the result of nature, almost always from a lightning strike, or in much rarer cases, lava if a volcano happens to be nearby. Now, for decades, scientists have been studying fire behavior in hopes of better understanding these notoriously unpredictable natural phenomena. And it's a complicated science. Weather is obviously a major factor here, whether it be wind, temperature, or humidity. Wind can not only push flames toward new fuel sources, it can also create more fuel by drying materials in moist areas. And as I mentioned, fires can actually generate their own wind with the upwelling of hot air that they create. This allows fresh air to fill the vacuum left behind, providing a new supply of oxygen. Things like sunlight and temperature can also help drive a fire. During the day, sunlight heats the ground and the warm air rises, allowing air currents to travel up sloped landscapes. And at night, the process is reversed. The ground cools and the air currents travel downward. As a result, fires often burn upslope in the day and downslope at night. Meanwhile, high humidity levels may be annoying for humans, but the extra moisture in the air can actually slow the spread of flames by dampening the fuel. Fires tend to burn less intensely at night because that's when the humidity is usually higher. Understanding factors like these has made us better at combating and preventing wildfires. Because, after all, we can't always let nature take its course. Fighting fires means eliminating one piece of the fire triangle, and the easiest piece for us to control is the fuel. So firefighting isn't always a matter of putting the fire out. Instead, it can just be a matter of finding a way for the fire to run out of fuel. To get in front of the threat, foresters often turn to prescribed burning, where fires are intentionally lit before the dry season to remove the dead wood and other fuel. Firefighters also use this strategy during a fire, setting blazes to destroy the fuel supply before the wildfire arrives. And of course, there's water. Now, I don't know if you know this, but water's really good at putting fires out. Water attacks all three parts of the fire triangle. It dampens wood and grasses, helping to reduce their usefulness as fuel. It cools things down both on the ground and in the air, reducing the amount of heat. And it helps block oxygen, mainly by creating steam in the air that helps push the oxygen away. However, water evaporates quickly, especially when a nice hot fire is around. So firefighters add things like gels to create what is basically sticky water that smothers fuels while also cooling them down. This mixture, or slurry, is often dropped from helicopters or airplanes. Some companies even throw in a dash of fertilizer to boost plants' recovery after the fire and dye it red so pilots can see where it's been dropped. But one important lesson that we've learned about fighting fires is when not to fight them. For most of the 20th century, foresters, at least in the US, tried to put out as many fires as they could, as fast as they could. And as a result, forests became overgrown with more small trees and shrubs below the canopy than you normally find with a natural fire cycle. So as a result, frequent smaller fires have been replaced by mega fires that are larger, hotter, and more severe. A study by the American Geophysical Union found that the number of large forest fires in 17 western states increased by about 7 per year between 1984 and 2011. The total area that these fires burned increased by more than 36,000 hectares each year. But as you might guess, the growing severity of forest fires isn't just the result of decades-old policy. Climate change is playing a larger role than ever. Our warming climate is causing higher temperatures, widespread drought, and earlier snowmelt, which causes earlier spring growth. It also allows infestations of insects like winged bark beetles to expand into new regions where they once couldn't survive. More infestations means more dead trees, and more dead trees means more fuel. So all of these factors put together may explain why, in the US, the 7 most severe fire seasons since 1960 have all occurred after the year 2000. And it's not just in the US. The outlook is looking pretty much the same elsewhere in the world. Recent studies predict that drier places in the middle latitudes and Australia will likely experience more fires in the long term. And not only that, but places at higher latitudes may also be at greater risk as time goes on. And that is because those places tend to have lots of carbon-rich peat soil, which can burn as long and as hot as coal. I am certainly not looking forward to the day when wild peat fires above the Arctic Circle become a regular thing. Thank you for watching this SciShow Infusion, especially to our Subbable subscribers. To learn how you can support us in exploring the world, just go to subbable.com/SciShow. And as always, don't forget to go to youtube.com/SciShow and subscribe.